Hello, everyone. What I want to do now is finish up talking about orthonormal bases. And basically, we're going to, in doing that, finish up talking about just Hilbert spaces in general, the theory of Hilbert spaces themselves. We will next dive into the basic theory of linear operators between normed vector spaces and Hilbert spaces. Okay, so as I mentioned in the first part, I'm going to prove the following theorem, or really corollary of what we did last time. But I definitely think it's worthwhile. It's worthy of being called a theorem. So let's say we have a closed subspace of a Hilbert space H. All right. So if we have an orthonormal basis, and let's say this here is a separable Hilbert space. Okay. So if we have an orthonormal basis for M, then for any x in my Hilbert space, the orthogonal projection is given by just what we had before if M is finite dimensional. So it's x en en. Okay. And before I prove this, I just want to make a quick comment. Remember that one of the homeworks is that H is a separable Hilbert space, so there exists an a countable orthonormal basis if and only if H is separable as a metric space. Okay, well, if M is a subset of this separable metric space, then M itself is a separable metric space. It's a subspace, so M is itself a separable Hilbert space, and thus an orthonormal basis, a countable rather orthonormal basis for M always exists. So, right, so there's no question of whether this even exists, this En. It absolutely does exist because M is itself a separable Hilbert space. Okay, and the proof is, maybe I'll just put this up here so that I can write the proof down here. Px is a sum. And the proof is surprisingly easy. It's just really, utilizing the fruits of our labor from the past few videos. It's really just one or two lines. Okay, right, so remember that certainly Px, no matter what x is, as long as it's in my Hilbert space, this is an M. And because we have a orthonormal, or I guess an orthonormal basis for M, that means that we can write Px, we can write anything in M as the following sum. Px is no different. It's Px en en. But we proved 2 videos ago, I believe, that we can move this P over here. In general, such operators are called self-adjoint or Hermitian. We'll talk about that soon. But anyway, so this is x P En inner product En, but because En is an M, and we know that P on M is just the identity. Px equals X if X is an M, or here particularly, Pen is going to be En because En is an M. And that finishes up the proof. This is simply n equals 1 to infinity, X En. Okay, right. Yeah, okay. So what I want to do next is talk about two applications. So actually in future homework, well, I'll talk more about applying this result to the Bergman space in a moment. So yeah, now I want to just discuss two applications of everything we've done. Just kind of remind you of an application to Fourier series and an application of what we're doing to the Bergman space. Particularly, we're going to carefully prove that we have a very canonical, very natural orthonormal basis for the Bergman space. And we'll talk about connections to general reproducing kernel Hilbert spaces and give another proof of what the reproducing kernel for the Bergman space is. All right, so first I want to talk about Fourier series. And I'm not going to really prove anything too difficult because all the proofs were done in bloody, gory detail in the harmonic analysis videos. I'm really going to emphasize using the main theorem from the last video, and how that gives us that exponentials give us an orthonormal basis for L2 of 0 to 1, and every function in L2 of 0 to 1 has a Fourier series that converges in L2. All right, so so actually these are the details I did not put in my harmonic analysis class. I basically said, well, by Hilbert space theory, we're done. So yeah, so it's definitely good to do those details here. So we need the following very easy proposition, which is, let's say H is a separable Hilbert space. And let's say En. So it looks very abstract, but it's almost tailor-made for the situation we're in Fourier series. So let's say we have an orthonormal, countable orthonormal subset of my Hilbert space. Particularly, these are going to be exponentials. And let's suppose that the span of all these, and I'll clarify what I mean by the span. In particular, I mean finite linear combinations of the ENs. So this is a set of all X in my Hilbert space, where X, for some big N, it's just a linear combination of N of these ENs. And these are just complex numbers, the lambda N's. So let's assume this is dense in my Hilbert space. So then the conclusion is this is enough to give us that this is an orthonormal basis And I guess really for Fourier series, I should go from n equals minus infinity to infinity, but whatever. It's just, this represents a generic countable orthonormal basis. Yeah, then this is an orthonormal. Whoops, sorry about that. Then this is an orthonormal basis, I guess, for H. And if proof is not hard at all, what is the proof? So this is often how you want to, in practice, prove something is an orthonormal basis. It's an incredibly useful proof strategy to do that, and that is to simply prove, well, one of the conditions that we know is equivalent to En being an orthonormal basis, and that is this equals 0 for all natural numbers n implies that x equals 0. All right, so this is our task here. If we do that, then from what we had in the last video, this will imply that En is an orthonormal basis for my Hilbert space. All right, so let's begin doing that. Let's say we start off with epsilon bigger than 0. And of course, I'm going to assume x is not equal to 0. If x equals 0, there's nothing to do. We have x equals 0, so assume x is not equal to 0. All right, so pick a y, or whatever you want to call it, m, doesn't matter. I'll use y. And the span of these ENs, we're assuming the span is dense, so I can always pick a y where this norm here is less than, just to get everything to be epsilon, let's do it epsilon squared over norm of x squared. And again, I'm assuming x is not equal to 0. If it is, there's nothing to do. Okay, so all we're going to do is look at the norm squared of x. We want to show that's going to be 0. If this is 0, then x is 0. Hilbert spaces are certainly normed vector spaces. So norm equals 0 means x is 0. So we write this as x inner product x, right? So that I can add and subtract a y in the second slot. Okay, so plus. So let's do something seemingly silly here. Well, this is non-negative. I mean, there's nothing really to that. Because this is equal to the norm of x squared, this is non-negative. So obviously it equals its own absolute value. And so now I can use a triangle inequality. That. Okay, and this here, well, I use Cauchy-Schwarz, norm of x. This is going to be the norm of x minus y. Leave this alone here. Oops, sorry about that. Should be a bracket there. Okay, well, this here, I'll use blue, I guess, is less than or equal to epsilon squared over yeah, I guess I really want epsilon squared over the norm of x. Not that it matters all that much, but right. So yeah, sorry about that. Right. So this is going to be less than just epsilon squared. Plus this right here. Right. And I claim that this is going to be equal to 0, this term right here. So I claim that this here equals 0. So this is going to be equal to epsilon squared. Why is this true? Well, let's say y is, I don't know, n equals 1 to big N of lambda n en. So this is going to be, just use linearity. So this is going to be lambda n complex conjugate x en. Well, we know what that is. We should know what that is. This is, oh, whoops, sorry about that. Big N, not infinity. So this is just 0. Because x, we're assuming, is orthogonal to every single one of these ENs, no matter what. Okay? Now, maybe you might object and say, well, you know, why, like, maybe we need to use larger n if x is really small and if epsilon is really small. So particularly absolutely big N and y are going to depend on x. The norm x gets closer and closer to 0. I need to, or rather, actually, sorry, if the norm of x gets bigger and bigger and bigger, then I need to pick y closer and closer and closer to x, because x in norm large forces this whole thing to be really large. So maybe that means big N is going to depend on x. Well, doesn't matter, because this is flat out 0. X is orthogonal to every single one of these, so I don't really care how big N depends on x. You're just adding up 0 finitely many times. So this is 0. And so all we basically, that proves it. Okay. So what did we prove? We proved that the norm of x squared is less than or equal to epsilon squared. Take the square root of both sides. So this is less than or equal to epsilon. We're going to add epsilon bigger than 0, implies x equals 0. All right. So, like I said, pretty straightforward proof. Really not too much to that. The real depth of this proof is that what's in red here, that if I can prove what's in red here, then we have En is a orthonormal basis. All right, so right. So let me remind you of the situation with Fourier series. Okay, so the situation with Fourier series is following. So let's define these exponentials here from n equals minus infinity to infinity. Sorry about that. And let's call this, let's say En of t. Right, so certainly each one of these is obviously an L2 of 0 to 1. They have modulus 1 identically. So and we've done this before. It's very easy to check that this is an orthonormal set. Each one of these has norm 1 and L2, and they're orthogonal to each other. En inner product Em for n not equal to m is 0. Okay, so recall that we define the partial Fourier series of a f, let's say an L2, just to be basically, the partial expansion of f, pretending that this is an orthonormal basis. So it looks exactly like that, just f inner product En, which remember is Fourier coefficients. So this is f hat of n, En of t. And remember that we defined sigma n to be the average of the nth Fourier series. And so when n, just to be clear, when we have, oops, sorry about that. I'll make this also big N. Doesn't really make sense otherwise. Yeah, so when big N here is 0, all that means is we have, well, it's just a constant f hat of 0, which is just the integral of f over 0 to 1. Right. So this is going to be, right, so we're taking the average right, so we're going to actually, sorry, it should be 1 over n plus 1. Right, we're taking the average of the partial Fourier series. Okay, and remember, from our harmonic analysis, videos, that we proved using the theory of approximate identities, that as n, big N goes to infinity, and this was called Dirichlet, not Dirichlet's theorem, it was called Feyre's theorem, that in fact in LP, because we proved facts about approximate identities in LP, when P is between 1 and infinity. So that implies that M equals the span of all these. Is dense. Well, it's really dense in all LP, but we're talking about Hilbert spaces, so we really don't care about LP other than L2. And why is that? Well, it's absolutely trivial, because well, maybe I'll just circle it. Well, sigma n for each n is in M. I mean, it's obviously, it's trivially, just by definition, a finite linear combination of these exponentials. Okay. So the fact that we can approximate any f in L2 by a finite linear combination of these exponentials means that, by definition, the span of these exponentials is dense in L2. So, right, like I said, this proposition here is basically tailor-made for Hilbert, for Fourier series, right? So this is dense. That means this is an orthonormal basis. So by the proposition we just proved, sorry about that, it matters, but like the same color. That, right, this is an orthonormal basis. Of L2. Right, and just to kind of remind you of what that means, kind of put this in perspective. For any f in L2, you can write f of t, just to emphasize Fourier series. It's not pointwise, but anyway. So this is going to be f hat n of t e to the 2 pi t, where the convergence is in L2. Okay, and again, remember that this here, the definition is f inner product the nth exponential on L2. Right, so yeah, that's the L2 theory of Fourier series. Right. Yeah, I mentioned in harmonic analysis that actually the pointwise convergence, so certainly because we have L2 convergence, there's a subsequence of these big N's where you have pointwise convergence. But actual pointwise convergence, as big N goes to infinity, that's extremely challenging. I mean, I could literally make an entire semester course easily on just proving that. It was proved in 1970, I think, 71. No one really understood it. And then it took and then there's another proof by the Fields medalist Charles Pfefferman in an Annals of Mathematics paper 10 years later that just reproved it. And then it took really another 10 or 20 years for anyone to really understand it well. But yeah, anyway. Okay. Right, so let me now talk about another application, and that's the Bergman spaces, and more generally to reproducing kernel Hilbert spaces. Okay, so I want to prove the following. I guess it's worthy of a theorem. I don't know, maybe it isn't, but whatever. So I claim that we have a very nice, easy, natural orthonormal basis for the Bergman space. Okay, and that's just these monomials. Okay. So I claim that this is an orthonormal basis. Okay, so we're going to implement the same proof strategy that we did in the proposition. So first of all, well, I just, yeah, so I don't want to write anything down, but just the fact that these here are orthonormal, that's an easy computation that you could do. It's really like a Calc 3 double integral computation. So, and the square root of n plus 1 is to make all these have norm 1 in your Bergman space. But yeah, so this is definitely an orthonormal basis. So I'm not gonna, sorry, this is definitely orthonormal. We haven't proved that it's an orthonormal basis. That's what we need to prove, but you can check that this is an orthonormal set in your Bergman space. Okay, so to prove that it's an orthonormal basis, what do we need to do? Well, again, it's the same strategy as before. Let's assume that each one of these equals 0. Now let's assume F is, let's say, in my Bergman space. So let's assume all of these are 0. So really, I should have a square root of n plus 1 here, but that's just a non-negative constant. So this is really what I need to prove. I can always pull out that non-negative constant, so it doesn't affect whether F inner product each one of these elements in my orthonormal set is 0. So. All right, and I want to show that this implies F equals 0, and this is not hard at all. Okay, so let me just write out what this is. 0 is going to be equal to this inner product. Whoops, sorry about that. And yeah, maybe make clear this is the Bergman space inner product. By definition, this is just this integral here, f of z, z bar to the n. So by dominated convergence theorem, and particularly your dominator would just be modulus f of z. Sorry about that. So yeah, by dominated convergence theorem, really you can write this as this limit here. R goes to 1 from the left. Don't really care about the 1 over pi, but I don't want to erase. So, so about that. So let's just integrate over the disk of radius r, center 0. Right. Where r is between 0 and 1, and r is going to approaching 1. And the reason why I want to do that is I know on this disk we have uniform convergence of the Taylor series centered at 0, because we're dealing with a subset of the unit disk where the closure is compact. So yeah, we're dealing with a set whose closure is a compact subset of the unit disk. So we know whenever we have that, we have uniform convergence of the Taylor series on such a set. That's just basic complex analysis. Okay, so this is going to be equal to the following limit. 1 Let's do n. Maybe n is not good. Let's do j. Let's say aj is just Taylor coefficient. Z bar n. Right, so now let's use uniform convergence for each fixed r. So bring out interchange to sum and integral. So this is going to be a j, z, j, z bar n. Again, a very easy Calc 3 integral shows you that just polar coordinates, that this is going to be 0 unless j equals n. That's complex conjugate. Sorry about that. Right, so there really is no sum. It's going to be an times r d, or this integral here, z to n, not j. All right, and so this is just going to be n times whatever this is. I don't even care what this is. I mean, it's going to be n plus 1, but whatever, doesn't matter. Yeah, so what have we proved? We proved that for any fixed, I don't know how to delete this, but anyway, whatever. Whatever. So what have we, yeah, let me get rid of this and put it on the previous screen. Sorry about that. So this is going to be equal to right, an. All right, so right, what have we proved? We've proved that, well, this here is 0. So if this is 0, this is n plus 1 here. So n plus 1 times an is 0 for any n. That means an is 0. And obviously that means f is identically 0. Yeah, we're saying the Taylor expansion of f on the unit disk is identically 0. So f has to be identically 0. Right. So that proves that we have a very nice orthonormal basis for the Bergman space. Okay, let me talk very briefly about connections to reproducing kernel Hilbert spaces. So I think 2 videos ago I talked about what reproducing kernel Hilbert spaces are. I'll just remind you what they are. So it's just a Hilbert space H of functions defined on some fixed set omega. Omega literally could be anything. And in machine learning and data science, you often implicitly assume omega is truly just about anything. Right, so you assume, the assumption is that point evaluation at each z is bounded, meaning absolute value or modulus of f of z, these are complex valued, is less than or equal to a positive constant depending on z times the Hilbert space norm of f. And that leads to a reproducing kernel. So because, remember from the Reese representation theorem, we called this, let's say, I forget what I called it, but maybe it was LZ. So for fixed z, this is a bounded linear functional, so that there exists an element in your Hilbert space where this bounded linear functional LZF is given by f kz in your Hilbert space. So this kz kind of, for each z, reproduces your Hilbert space in this sense. Okay, so a fairly easy homework is the following really nice result. If H is a separable, well, I wrote that. Well, I guess, okay, I probably should have done that. So let's say we have a separable reproducing kernel Hilbert space. And in practice, all reproducing kernel Hilbert spaces are separable. And we have an orthonormal basis. Then we have the following. So just a reminder that each kz is in my Hilbert space. So for fixed z, kz is itself a function on omega. So to denote that, remember what we did. We said kz of w was k, let's see. Yeah, so kwz. Okay. Or rather, we kind of define kw of z to be kz of w. So we're defining this function of two variables, w and z, and omega times omega, by kz of w, or kz is this fixed element in my Hilbert space of functions on omega. Anyway, so we can explicitly write down the reproducing kernel. And the beauty of this is it doesn't matter what orthonormal basis we choose. They all give us the same result. That this is given by En of W, En bar, complex conjugate of Z. And if you can see the trick to proving this, not really a trick, but you might be able to just see it. It's very straightforward. I don't want to give any hints because really I can't give a hint without telling you how to do it. And maybe to clarify, if Z is fixed, the convergence of this infinite sum is in H, okay? All right, so let me show you how this is often useful in practice, particularly for studying holomorphic function spaces. I think I mentioned that in data science, you really never want to figure out what the reproducing kernel is, you basically are always given the reproducing kernel. You always in data science start off with the reproducing kernel. Yeah, if anyone's, as I said, if anyone's interested in that, I could probably make a lecture or two on the whole kernel trick in data science. You know, it's basically you can use it to get a nonlinear version of you know, standard least squares regression, principal component analysis, and many of your other favorite algorithms and statistics and data science. But yeah, you always start off with a kernel K, but definitely in holomorphic function spaces, you know, it's you often start off with an orthonormal basis. So in particular, let's say you forgot, maybe you did forget what the reproducing kernel for the Bergman space was from 2 videos ago. Let's say you just completely forgot. Let's rederive what the reproducing kernel is using the fact that we have this orthonormal basis and using this result right here. All right. So as an example, for the Bergman space, remember En was given by n plus 1 to square root, so 1/2 z to the n. So let's just plug and chug and compute, and let's see what happens. See what we get. Well, again, if you remember from 2 videos ago, you know what we're going to get. But if you forgot, then let's see what we're going to get. All right, so this is by definition En of W, En bar of Z. So we have n plus 1 times n plus 1. N equals 0 to infinity. N plus 1, W to the n, Z bar to the n. Well, that's really just W Z bar to the n. Okay, now I want to be very rigorous here. So obviously you can figure out what this is pointwise for W and Z bar in the unit disk. I trust that you can do that. That's just playing around with a finite geometric sum. I mean, you really differentiate the finite geometric sum, but rigorously, we have convergence for fixed Z in L2. Okay. So for Z fixed, what do we really have based on the homework? We really just have the following. We have this here. To the n. In my Bergman space, well, that's exactly the same thing as saying in L2 of the unit disk. Okay, now we have convergence for fixed Z in L2. So then we have a subsequence converging in L2, or rather, sorry, we have a subsequence converging pointwise. Or pointwise almost everywhere. So let's do Kn. For almost everywhere, W. Right, so we have convergence almost everywhere. Okay. Right, but point-wise, and the Kn just denotes a generic subsequence. But by just playing around with the finite geometric series formula, we obviously know what. Sorry about that. I'll leave it at that. We obviously know what this is going to be equal to. Not just almost everywhere, but for all W. This limit here, it just trivially, as long as Kn goes to infinity as big N goes to infinity, this is going to be equal to just 1 over 1 minus. And again, it's nothing deeper from here to here than playing around with the finite geometric series formula. You just differentiate your standard finite geometric series formula. So it's W, whoops, sorry. Put the bar in the wrong spot. It's very easy to do when you do holomorphic function space theory. Right, so what do we have? For almost every W, kw of z, and for fixed z is going to be equal to 1 over 1 minus w z bar squared. Well, we know kw is holomorphic. This is for fixed z, this is in the Bergman space. So we know that this is true for all w. And this was true for all fixed z. So for all w and z, we have that k w z is going to be equal to 1 over 1 minus w z bar squared. Okay, right. All right, so I think I'll end there. Maybe it might be one or two results more for Hilbert spaces that will be homework, but basically we've taken care of the entire theory of Hilbert spaces. And now it's on to some of the more basics of normed vector spaces and Banach spaces, and the basics of operator theory. In particular, we're going to do chapter 2 next, the basics of linear operators, and I'm going to try to go through that fairly quickly. All right, hopefully this was useful. So long, take care, have a good weekend. Bye-bye.